Hello, this is part two of the lecture about non-singular matrices. So this theorem makes a connection between the identity matrix and this calculation that we call row reduction. And with this theorem tells us, it says, suppose we have a square matrix A whose RREF is denoted as B. Then we say that A is non-singular if and only if its RREF is the identity matrix. So this theorem provides a two-way equivalency between the identity matrix, right? So um, this is the implication of having if and only if. So this is telling us that A row reduces. So we write an arrow there and write RREF. This tells us that A row reduces to I, where I denotes the identity. Okay, so it says that if this happens, if A row reduces to I, then A is non-singular. Okay, and it also tells us that if A is non-singular, then we have that A row reduces to the identity, right? So it's an if and only if statement, and it will be very useful. So here we consider this 3 by 3 matrix, and the calculation of the RREF of this 3 by 3 matrix leads to this matrix here, and what we can see right away is that what we have here is that A does not reduce. We write an arrow and we can trash that arrow, and this means A does not row reduce to the identity, and therefore we would conclude that this matrix is singular, is not non-singular, therefore this matrix would be singular. Here's another example, and the RREF of this 3 by 3 matrix row reduces. The RREF is in fact the identity, so in this case we have that A, we write this A arrow I, and this arrow has RREF, meaning that A row reduces to the identity matrix. And so in such case we would say, oh, indeed, this matrix A is non-singular. Now, the null space of a singular matrix, we have a couple of comments. So given this 3 by 3 matrix, we can row reduce, augment with a column of zeros, row reduce, and find that the null space is given by this set. Exactly, the null space of the matrix is exactly equal to the solution set of the, so this is exactly equal to the solution set of the linear system that has the matrix A as the matrix of coefficients, and it has a vector of zeros. So this null space has infinitely many elements. There are absolutely a large number of members in this set. Now we consider the coefficient, this coefficient matrix, this matrix 3 by 3, as the coefficient matrix of the homogeneous system that has 0 as the vector of constants. And in this case, the null space contains only the trivial vector, only the trivial solution. So we're trying to underscore, illustrate the point that the fact that this matrix, in this case, the null space of the matrix has infinitely many elements, and this is related to the fact that A is singular. And we have already established why A is singular, right? So we had um, verified that we know that A does not row reduces to the identity, right? A does not row reduces to identity. A is singular, and so the fact that A is singular is directly related with having a null space with infinitely many elements. There are multiple elements of the null space, including the trivial vector, but there are infinitely many elements. So that is the connection, or that is the point we're stressing here. Null space of a singular matrix is a set that contains infinitely many elements, while the null space of a non-singular matrix. So we had established that this matrix A row reduces to the identity, right? So the RREF of this matrix is the identity, the 3 by 3 identity, and therefore A is non-singular. So the fact that A is non-singular, this is directly related to the fact that the null space of that non-singular matrix contains only the trivial element, only one single member of that set. Here are a couple of additional theorems. So if we have a square matrix, that matrix is non-singular if and only if the null space contains only the trivial solution. It only contains a vector of zeros. And if a square matrix, if a matrix is square, it's non-singular if and only if um, the linear system that has that matrix and an arbitrary vector of constants has a unique solution for each choice of that vector of constants. This theorem is called the non-singular matrix equivalences. There will be, we will revisit this theorem several times, but it is important that you start realizing how the fact that these are equivalent statements means that 1, 2, 3, and 4, they are each of them implies all the other three. So if A is non-singular, that implies that A row reduces to the identity. A non-singular implies null space has only a zero vector, and that also implies that um, a system, a linear system with that matrix as a coefficient, matrix of coefficients, will have a unique solution provided for every single choice of the vector of constants. So all these four statements are equivalent to one another, and each of them implies the other three.